The universe had a head start. Billions of years before Earth even formed, stars were already burning, planets already cooling, chemistry already experimenting with life. If intelligence can emerge even once, it should have happened thousands, maybe millions of times before us. Which means something doesn't add up, because a single advanced civilization, given enough time, could spread across the entire galaxy. Not in eternity. Not even in billions of years. In a fraction of that. So where is the evidence? No probes drifting through our system. No artificial signals cutting through space. No colossal structures rewriting the night sky. Just darkness. Just silence. And the deeper scientists look, the more uncomfortable the possibilities become. Maybe civilizations always destroy themselves. Maybe something out there is preventing them from growing. Or worse, maybe the silence isn't empty at all. Maybe it's intentional. Tonight, we're diving into most disturbing explanations ever proposed. Ideas that challenge everything we assume about life, intelligence, and our place in the universe. The year was 1950. At Los Alamos National Laboratory, a group of physicists sat down for lunch. Among them was Enrico Fermi. And in the middle of a casual conversation, he asked something so simple, it still hasn't been answered. Where is everybody? Enrico Fermi was not the kind of man who asked questions casually. He was one of the architects of the atomic age, the physicist who oversaw the first self-sustaining nuclear chain reaction beneath the stands of Stagg Field in Chicago in 1942. He understood scale, he understood probability. He understood what large numbers implied when you followed their logic to the end. The lunch at Los Alamos happened in the summer of 1950. Fermi was walking to the cafeteria with 3 colleagues, Edward Teller, Herbert York, and Emil Konopinski. The conversation was light. Someone had recently made a joke about flying saucers in a New Yorker cartoon, and there had been a string of UFO reports in the news. The 4 men were laughing about it. They sat down with their food. The conversation moved on to other things. Then Fermi asked the question. He was not asking about flying saucers. He was asking about mathematics. He had been doing the arithmetic in his head the way he always did, and the numbers had led him somewhere that did not make sense. The Milky Way is old, older than most things we can name. Old enough that a civilization emerging anywhere in it, even billions of years ago, would have had time to spread, to colonize, to leave evidence so overwhelming that we could not possibly miss it. A civilization traveling at 1% of the speed of light, a pace so conservative it barely qualifies as interstellar ambition, would cross the entire galaxy in somewhere between 10 and 100 million years. That sounds like an incomprehensible span of time, until you compare it to the age of the galaxy itself, 13.6 billion years. 100 million years is less than 1% of that. The galaxy has had time for this expansion to happen not once, not 10 times, but hundreds of times over. The sky above Fermi's lunch table should have been crowded with the evidence of that expansion. Signals, structures, the footprints of engineering on a scale visible across stellar distances. Something. There was nothing. His colleagues understood immediately what the question meant. Not, are there aliens? But, given the mathematics of time and space and probability, where is the evidence that should be everywhere? The silence was not a gap in the data. It was itself a data point, and it was the most important data point in the history of the search for intelligent life. Fermi died in 1954 without an answer. The question carried his name forward. Michael Hart formalized the argument in a 1975 paper, laying out the logic so rigorously that it became impossible to dismiss as casual speculation. If interstellar travel is physically possible, and if civilizations arise with any regularity, the galaxy should be colonized. The fact that it is not, and demonstrably, requires an explanation. Every explanation that has been proposed in the decades since is either terrifying, bizarre, or both. The instrument that has made this question most urgent is not the one built in New Mexico in 1960, though that was where the formal search began. The instrument that changed everything was launched on Christmas Day, 2021, and has spent the years since dismantling every comfortable assumption the field had assembled. The James Webb Space Telescope has found galaxies that formed when the universe was 280 million years old. It has found oxygen in galaxies that existed when the universe was 300 million years old. Oxygen that should not exist because the stellar generations required to forge it had no time to complete their cycles. It has cataloged nearly 800,000 galaxies in a patch of sky 3 times the size of the full moon. It has made the 2 trillion galaxy estimate not a theoretical projection, but a number you can approach from the data. Every galaxy Webb reveals is a candidate. Every star in every galaxy is a candidate. Every planet around every star is a candidate. The universe keeps expanding the population of possible origins for intelligence, and the silence in response keeps expanding in proportion. The question Fermi asked over lunch now carries more weight than it did when he asked it. The tools are better, the numbers are larger, the search has been longer, the result has not changed. 0. That number deserves everything that follows. Frank Drake was 29 years old in April 1960 when he pointed an 85-foot radio telescope at 2 nearby stars and listened. The stars were Tau Ceti and Epsilon Eridani, chosen because they were close, because they were similar in type to our own sun, and because they sat at the frequency Drake had selected as the most logical channel for interstellar communication, 1,420 megahertz, the emission line of neutral hydrogen, the most abundant element in the universe. The logic was elegant. Any technological civilization would know about the hydrogen line. It was the obvious place to listen. Drake called the project Ozma, after the Queen of the Land of Oz, and over roughly 150 hours, he heard almost nothing. At one point, a strong pulsing signal came through and the team went rigid. It turned out to be a high-altitude aircraft. The rest was silence. Ozma found nothing, but it established that the search was possible, that the tools existed, and that the question deserved more than a lunch table. The following year, in November 1961, Drake convened a conference at Green Bank, West Virginia, to take stock of the field. 10 people attended, including Carl Sagan. The group included astronomers, physicists, a neuroscientist, and a dolphin communication researcher whose presence signaled how seriously they took the problem of intelligence in forms other than human. They spent the conference working through a framework Drake had sketched on a blackboard that morning, a way of organizing everything they did not know about how common intelligent life might be. He wrote it as an equation. Not an equation in the mathematical sense, not a formula that spat out a precise answer when you plugged in the numbers. It was a framework, a way of decomposing ignorance into components so that you could see clearly what you were guessing at and what you actually knew. The Drake equation multiplied together a chain of probabilities and rates. The rate of star formation in the Milky Way, the fraction of those stars with planets, the fraction of those planets that could support life, the fraction where life actually emerged, the fraction where intelligence developed, the fraction where intelligence built technology capable of detectable communication, and finally, the average lifespan of such technological civilizations. At the conference in 1961, working through those factors one by one, the group arrived at estimates ranging from 1 communicating civilization in the galaxy to millions. The range told you everything about how little anyone knew. But the structure of the equation told you something else, something more important, where the uncertainty lived and what it would take to reduce it. In the decades since, every variable that could be measured has been measured, and every measurement has moved the estimate in the same direction. Drake and his colleagues guessed that the fraction of stars with planets was roughly 1 in 5. They were being generous. Many astronomers at the time believed planets were uncommon, that planetary formation required unusual conditions, that our solar system might be a rarity. Between 2009 and 2018, the Kepler Space Telescope stared at approximately 150,000 stars and watched for the tiny dips in brightness caused by planets crossing in front of them. Kepler confirmed thousands of exoplanets. The statistical analysis from that mission produced a result that rewrote the equation. Virtually every star in the Milky Way has at least 1 planet. The fraction did not go from 1 in 5 to 1 in 2 or 3 in 4. It went to essentially 1. every star. The number of potentially habitable planets, those sitting in the zone where liquid water could exist on a rocky surface, was estimated from Kepler data at roughly 40 billion in our galaxy alone. 40 billion worlds where the chemistry of life might in principle begin. That is approximately 5 planets for every human being alive on Earth today. This was supposed to simplify the paradox. More planets meant more chances. More chances meant more life. More life meant more civilizations. More civilizations meant more signals. Instead, it made the silence catastrophically louder. Because the number on the other side of the equation had not changed. Every improvement in telescope sensitivity, every widening of the search, every increase in the number of candidate stars surveyed had produced the same answer: nothing. As of early 2026, the Breakthrough Listen program had scanned approximately 1 million nearby stars. The Commensal search system, running alongside the Very Large Array in New Mexico, had covered more than 950,000 fields in its first 11 months alone. But the Murchison Wide Field Array in Western Australia had surveyed 2,800 entire galaxies, not individual stars, for any sign of large-scale technological activity. The accumulated data represented more computing power, more telescope time, and more systematic coverage than anything Frank Drake could have imagined pointing his 85-foot dish at 2 stars in 1960. The number at the end of every pipeline was the same number. Statistical models built on 6 decades of null results now constrain the number of detectable technological civilizations in the Milky Way to fewer than 1 to 5 per century across the entire galaxy. That is not a shrug. That is not a non-result. That is a measurement, the most important measurement in the history of astronomy, and it is telling us something that the Drake equation, for all its organizational elegance, was not built to say clearly. Something is wrong. Either the equation's variables are far more hostile to life than anyone estimated, or there is something about the later stages of the chain, the development of intelligence, the survival of civilizations, the duration of their detectable phase, that we have systematically failed to account for. A barrier exists somewhere between chemistry and communication. A filter, something that most beginnings never get through. Robin Hanson named it in 1996, and the name he chose was exactly right. Robin Hanson was an economist at George Mason University when he published the paper that reframed everything. He was not an astronomer, he was not a physicist, and he looked at the Fermi paradox the way an economist looks at a market that is producing outcomes inconsistent with the incentives, and he asked the most precise possible version of the question. If the galaxy should be full of civilizations, and it is not, then somewhere between dead rock and an interstellar civilization, there is a step so improbable that almost nothing gets through. He called it the Great Filter. The concept does not require knowing which step it is. It requires only accepting that the silence proves the filter exists somewhere in the chain. The mathematics demands it. If every step from chemistry to starships were reasonably probable, the galaxy would be visibly colonized. It is not. Therefore, at least one step has a pass rate so close to zero that the product of all probabilities collapses to near nothing. Yet the filter could sit anywhere. It could be the origin of life itself, the emergence of the first self-replicating molecule from raw chemistry, a step so improbable that it has happened perhaps once in the observable universe. It could be the development of the complex eukaryotic cell, the kind with a nucleus and specialized internal machinery, a step that took Earth nearly 2 billion years to achieve after life first appeared. It could be the emergence of multicellular organisms, a transition that the fossil record shows required another billion years of single-celled predecessors. It could be intelligence itself. It could be technology. It could be survival. The question that carries real weight is not whether the filter exists. The silence answers that. The question is whether the filter is behind us or ahead. If the filter is behind us, somewhere in the early steps of the chain, then we are extraordinarily rare but safe. We have already cleared the hardest barrier. The silence around us is the silence of a galaxy in which almost nothing else made it through. We are the exception. The hard part is over. If the filter is ahead of us, then every civilization that reaches our level eventually hits a wall it cannot survive. The galaxy is not empty. It is a graveyard. Every civilization that built radio telescopes and asked where everyone was, every civilization that developed nuclear reactors and digital computers and the capacity to reshape its own genome, collapsed before it could spread. We are not the exception. We are the next in line. Hansen laid this out with the precision of someone who understood probability. Let's imagine 100 civilizations starting the journey from simple chemistry toward interstellar travel. If the filter is behind us, 99 of them never made it past microbial life. We are the one that got through. Dangerous, in the sense that the universe appears nearly sterile. But done. If the filter is ahead, all 100 developed technology. 99 are gone. We have built the rockets and the radio telescopes. We have not yet crossed whatever line kills the others. For 2 decades after Hansen's paper, the optimists had the stronger case. They pointed to the genuine difficulty of the early steps. Earth spent roughly 2 billion years locked at the single-celled stage before the transition to complex cells. It spent another 1.5 billion years before multicellular organisms appeared. These are not brief delays, and they are most of the planet's history. The probability of clearing each transition might be genuinely low enough to explain the silence without requiring that something catastrophic awaits every civilization that reaches our level. Then, in 2024 and 2026, 2 papers landed that shifted the weight of evidence sharply toward the darker interpretation. Both proposed filters ahead of us. Both described mechanisms already visible in human data. And together, they suggested that the comfortable view, the view in which the hard part is behind us, was the one that required the most extraordinary assumptions. The comfortable view was always the one you had to argue for. The dark view was always the one the numbers naturally produced. Before examining what might kill civilizations that reach our level, it is worth understanding what the James Webb Space Telescope has done to the earlier parts of the chain. Because the discoveries coming from Webb have not made the filter question simpler. They have made it stranger. The telescope has found galaxies that existed 280 million years after the Big Bang. It has found oxygen in those galaxies. Oxygen that required multiple complete cycles of stellar birth and death to forge, cycles that take millions of years per generation, cycles that should not have been completed in the time available. The galaxy called MOMZ-14, confirmed spectroscopically by a team at Yale in May 2025 from data inside the Cosmos Webb survey, blazes across 13.5 billion years of space and arrives at Webb's mirror still detectable, and it was forming stars at a furious rate in the first sliver of cosmic history. The universe was barely an infant, and already producing the raw materials for chemistry, for planets, for life. What this tells us is that the universe was not slow to produce the conditions for life. It was in a hurry. Massive stars burned bright and brief, seeding their surroundings with heavy elements. The first rocky planets could have formed within the first 1 billion years after the Big Bang, in galaxies that had already undergone multiple cycles of stellar enrichment. The chemistry of life is not exotic. It requires carbon, oxygen, nitrogen, hydrogen. The universe began manufacturing all of these in industrial quantities from the earliest chapters of its history. The Cosmos Webb survey, which cataloged nearly 800,000 galaxies across a patch of sky 3 times the size of the full moon, revealed something else that matters for the Drake equation. The structures we call galaxy clusters, the gravitational cities where matter accumulates and stars concentrate, were assembling themselves far earlier than models predicted. The protocluster JD-ESID-1, confirmed in a paper in Nature in January 2026, contains at least 66 potential galaxy members and carries a total mass of roughly 20 trillion solar masses. Its light left when the universe was barely over 1 billion years old. A galaxy cluster of that scale and that maturity should not exist at that age, according to the standard models. It does. The implication for the Fermi paradox is uncomfortable. If rocky planets have been forming in chemically enriched environments for most of the universe's 13.8 billion year history, the first technological civilizations did not arise 5 billion years ago when Earth formed. They could have arisen 10 billion years ago, 12 billion years ago. Civilizations that predate our solar system by billions of years would have had time not just to colonize the Milky Way, but to colonize it, develop for billions of years, and leave evidence visible from across intergalactic distances. We see nothing, not just nothing from civilizations of our era, nothing from the civilizations that should have preceded us, by a span of time so vast that our entire evolutionary history, from the first stirring of life to the present moment, could fit inside it 1,000 times. Yet the JWST data does not make the paradox go away. It makes the paradox geometrically larger. The denominator of available time and available planets has grown. The numerator of observed evidence has not moved. This is the context in which every proposed solution to the Fermi paradox must be evaluated, not just against the galaxy as we knew it, against the galaxy as Webb is revealing it, a galaxy that has been capable of producing intelligent life for most of its history, a galaxy that has produced exactly the signals and structures we would expect from intelligent life, which is to say, none. The most reassuring category of explanation for the silence is the one that says the hard part is already behind us. The filter is in the past. Life, intelligence, and technology are extraordinarily rare achievements, and Earth managed them through a combination of circumstances so improbable that in a galaxy of hundreds of billions of stars, we might be one of a handful, or the only one. This class of argument is called the rare Earth hypothesis, named after a 2000 book by Peter Ward and Donald Brownlee at the University of Washington. Their case rested on a cascade of requirements. Complex life needs a stable climate. A stable climate needs plate tectonics to regulate the carbon dioxide cycle. Plate tectonics requires a specific internal heat budget and mantle composition. It requires a planet in a stable orbit around a stable star in a stable region of the galaxy. It requires a large moon to stabilize the axial tilt and prevent the kind of chaotic rotational wobble that would make surface temperatures unpredictable. And it requires a Jupiter-sized planet in the outer system to sweep the inner system of the asteroid bombardment that would otherwise sterilize the surface. The list went on, and each item on the list was a potential filter. Miss any one of them, and you do not get complex life. You might get bacteria forever. You might get nothing. For 15 years, rare Earth was the standard scientific argument for why we might be alone. It fit neatly with the Fermi paradox. If the geological and orbital requirements for complex life are an improbable accident, the silence is explained by the fact that almost nobody else won the lottery. We are the statistical outlier, not because life is rare, but because everything life needs to climb from microbes to megastructures is rare. Then the models started to disagree. At computer simulations conducted between 2015 and 2024, gradually undermined the neat causal chains that rare Earth depended on. Some models showed that plate tectonics on Earth might not have preceded the emergence of complex life. Instead, tectonics may have arisen in part because of complex life. Biological activity on the surface, particularly the weathering of rocks by early organisms, may have weakened the crust enough to allow subduction to begin. If the relationship is partly reversed, if life does not need tectonics but tectonics needs life, then the filter is not geological. The requirement disappears. Other simulations showed that plate tectonics can actually slow the oxygenation of the atmosphere by pulling oxidized material back into the mantle. The process that rare Earth argued makes complex life possible may in some configurations delay it. The theoretical framework was not wrong so much as it was incomplete, and incompleteness in one direction tends to infect the rest of the argument. Then there was Pluto. When NASA's New Horizons spacecraft flew past the Pluto system in 2015, it returned images that stopped planetary scientists cold. Pluto's surface showed evidence of geological activity, fractured plates, convective overturn in a glacier of nitrogen ice spanning a region larger than Texas. Charon, Pluto's largest moon, showed similar features. These are worlds billions of miles from any star's warmth, receiving roughly 1,000th of the solar energy that Earth receives. Nobody predicted active geology there. The discovery did not prove that plate tectonics are common, but it demonstrated that geological activity can emerge in conditions far outside the narrow window that rare earth proposed as the minimum requirement. The most pointed challenge came from the updated abiogenesis data. Research published between 2023 and 2025 showed that amino acids and RNA nucleotides, the molecular building blocks of life, likely co-evolved from the very beginning of prebiotic chemistry rather than appearing in sequence. They emerged together, interacting in ways that made both more stable and more functional than either would have been alone. The origin of life is not the story of one molecule getting lucky in a very particular chemical environment. It is the story of a system of molecules bootstrapping itself into existence through cooperative chemistry. That matters enormously for rare earth. And if the origin of life is not a needle in a haystack event, but something more like a ratchet, a chemical process that tends to click forward wherever conditions allow, then life is not the rare achievement. Life is the easy part. Life appeared on Earth almost immediately. The planet formed approximately 4.54 billion years ago. The last universal common ancestor of all life on Earth, the single organism from which everything alive today descends, existed approximately 4.2 billion years ago. The gap is somewhere between 300 and 400 million years, and much of that window was spent under conditions where life as we understand it could not have survived on the surface. The planet was partly molten. Asteroids bombarded it relentlessly, yet life appeared as soon as conditions allowed it. And possibly sooner. Compress the entire 4.54 billion year history of Earth into a single calendar year. The planet forms on January 1st. Life appears before the end of February. Dinosaurs do not show up until December. Humans arrive in the final minutes of December 31st. February. That is how quickly non-living chemistry became biology on this planet. If abiogenesis is that robust, that fast, that willing to begin in imperfect conditions, then it is probably happening across the 40 billion habitable worlds in the Milky Way right now. Probably it happened on the rocky planets that formed in chemically enriched environments 10 billion years ago. But here is the number that does not follow from the optimism about early life. Intelligence took another 4 billion years. Life appeared in February, but intelligence appeared in the last minutes of December. Whatever filter governs the emergence of minds capable of building radio telescopes, it is not the origin of life. That step appears to be relatively easy. Whatever filter matters is somewhere in the 4 billion year gap between the first microbe and the first physicist. In 2024, two researchers named Stern and Gerrier published a paper that targeted the variable in the Drake equation that had always been the most optimistic, the fraction of planets with life that go on to develop intelligence. Drake's original estimate treated this fraction as close to 100%. If life starts, evolution is relentless. Given enough time, something smart will emerge. Intelligence seemed like a natural endpoint, almost inevitable once biology was established. As Stern and Gerrier argued, it was not. Their analysis estimated the fraction of life-bearing planets that develop intelligence at between 0.003% and 0.2%, between 3 in 100,000 and 2 in 1,000. Their reasoning was geological and ecological. Intelligence on the scale that leads to technology requires specific planetary conditions, sustained over very long time periods. You need 500 million years or more of continuous plate tectonics to regulate the long-term carbon cycle in ways that prevent runaway warming or cooling events that would reset the evolutionary clock. You need a particular ratio of continent to ocean that allows complex ecosystems to develop on land, rather than remaining confined to water where the energy gradients are different. You need geological stability over timescales that most planets simply do not provide. To make that probability tangible, consider a jar filled with 100,000 marbles. Under Stern and Gerrier's lower estimate, 3 of those marbles represent planets where life develops intelligence. Under their upper estimate, 200. Compared to Drake's original assumption that nearly all 100,000 marbles would qualify, the difference is not a revision. It is a collapse. If intelligence is that rare, the silence starts to have a natural explanation. 40 billion habitable planets in the Milky Way sounds like an enormous number until you multiply it by 0.003%. That gives you roughly 1.2 million planets with intelligent life across the entire galaxy. It's spread across 13.6 billion years of history. Divide by the galaxy's lifespan to get the number present at any given moment, and the number shrinks to something close to nothing. But Stern and Gerrier's argument has a weakness that cuts both ways. If the requirements for intelligence are that specific, then we ourselves are a statistical miracle. Every step of our evolutionary history, the development of the eukaryotic cell, the Cambrian explosion of multicellular complexity, the emergence of vertebrates, the development of large-brained social primates, the invention of language, required the specific geological and ecological conditions to persist for the required duration. The requirements were met here, on Earth, around an ordinary star and an ordinary spiral arm of an ordinary galaxy. And if those requirements are so demanding that they are met on only 3 in 100,000 habitable worlds, we are living proof that the universe occasionally produces extraordinary things from ordinary materials. That possibility, strange as it sounds, is the optimistic reading. We are extraordinarily rare. The silence is explained by the fact that almost nobody else made it through the intelligence bottleneck. The filter is behind us. The hard part is done. The pessimistic reading is that we are not rare at all, that intelligence is more common than Stern and Gerrier estimate, that millions of civilizations have arisen across the history of the galaxy, and that the filter is not in the emergence of intelligence, but in what intelligence inevitably does next. Michael Garrett is an astrophysicist, not an economist. When he published a paper in 2024 proposing that artificial intelligence is the great filter, the argument was not philosophical. It was built on a timeline. Earth's first radio transmission occurred in 1895, when Guglielmo Marconi sent signals across a distance of roughly 1 mile. 127 years later, in 2022, generative artificial intelligence systems began operating at a level that surprised even their creators. Systems that could write, reason across domains, generate images, and solve problems that had been considered benchmarks of human uniqueness. The jump from first radio wave to sophisticated artificial general intelligence took just over a century. Garrett's model assumes that any technological civilization follows a similar trajectory, not because alien civilizations would be identical to ours, but because the underlying pressures are universal. Once you develop electronics, the path toward increasingly capable autonomous computing is not a choice. It is driven by economic competition between groups within the civilization, by military advantage, by the basic logic of tool improvement. Every system you build can be used to build a better system. The ratchet does not reverse. His estimate for the window between developing artificial intelligence and being fundamentally transformed or destroyed by it is roughly 200 years. That is not the window during which a civilization might build interstellar ships or send detectable signals. That is the total duration during which a civilization might exist in a form that would produce those things. Apply that window to the Milky Way, the galaxy is 13.6 billion years old. A civilization's detectable phase lasts 200 years. That is like trying to photograph a specific lightning bolt during a thunderstorm that lasts 4 million years. Even if millions of civilizations have arisen across the galaxy's history, the probability that any two of them would be broadcasting at the same time is vanishingly small. The model does not require artificial intelligence to physically destroy a civilization. It only requires that the civilization change into something so different that it no longer produces the kind of signals we would recognize or the kind of structures we would detect. A species that merges with its machines stops being the kind of thing that builds radio transmitters and points them at other stars. A species replaced by its machines leaves behind systems whose goals and communication methods have nothing in common with the biological progenitors. In either case, the observable signature disappears. The civilization goes dark. Look at Earth's own trajectory as a test case. Military radar, the loudest signal our planet produces, operates at roughly 10 to the 14th watts in directional bursts. Those signals are detectable by a Greenbank-class telescope from about 200 light-years away. But we are already shifting toward fiber optic cables that carry data through glass rather than through the air. Cellular networks use low-power transmitters aimed at the ground. Digital signals are compressed and encrypted, which makes them indistinguishable from random noise to a distant receiver. Military radar is shifting to phased arrays that focus energy in tight beams, rather than spraying it in all directions. Earth in 1970 was a bonfire visible from miles away. Earth in 2026 is a flashlight pointed at the floor. We are not moving toward louder, we are moving toward silent. Within a few decades, our unintentional radio emissions may drop below the detection threshold of any realistic alien telescope. We are closing our own window from the inside, not because we are dying, because we are becoming more efficient. If Garrett is right about the 200-year window, and if Earth is currently approximately 127 years into that window, the arithmetic of our own situation acquires a quality that is difficult to look at directly. We have roughly 70 years, not 70 years until extinction, necessarily. 70 years until the transition, until the civilization that builds radio telescopes and points them at the sky has become something else, something quieter, or something gone. Darren Dugan's paper appeared in February 2026, and the filter it described requires none of the drama of artificial intelligence or nuclear war. It requires only one thing: a species smart enough to decouple reproduction from survival. The argument is built on demographic data that no government on Earth is able to reverse. South Korea's total fertility rate in 2024 was 0.72. That means for every 2 adults, fewer than 1 child. Replacement level is 2.1. South Korea is not at half replacement. It is at 1/3. Japan's at 1.2. Italy at 1.24. China fell below replacement in 2022 and is accelerating downward. The United States fell below replacement in 2021. These are not projections from a model with uncertain parameters. These are census numbers, counted, verified, published. Dugan's model does not treat fertility decline as a political problem with a political solution. He treats it as a thermodynamic inevitability, the same way entropy is inevitable. His argument works like this. In any species that evolves intelligence, individuals eventually gain the ability to choose whether to reproduce. Once that choice exists, the calculus shifts. In a subsistence society, children are labor, investment, insurance. In a technological society, children are expensive. They cost time and money and career progression and sleep. The returns are emotional rather than material. And emotional returns compete with every other source of satisfaction that advanced technology provides. The species that built the global economy also built the most effective substitute for the ancestral reasons to have children that has ever existed. Every government that has tried to reverse the trend has failed. Pronatalist policies in Scandinavia, in Japan, in Singapore, in Hungary have produced temporary bumps of a few percentage points before the decline resumed. France, which runs the most generous family support system in Europe, still fell below replacement. The trend does not respond to incentives at the scale governments can deploy. It is not a policy failure. It is a structural property of what advanced societies do to reproductive motivation. And Dugan's projection maps current global trends forward with a straightforward model. Human population peaks around 2080 at roughly 10 billion. Then the decline begins. Each generation is smaller than the previous. The rate of decline accelerates because a smaller population of reproductive age adults produces an even smaller next generation. By 2500, the model estimates fewer than 100 million humans. By 3000, functional extinction. The physical comparison he reaches for is bacterial. A petri dish colony that consumes all available nutrients and dies. But Dugan's filter is worse than starvation. In the petri dish, the bacteria run out of food. In his model, the food is still there. The resources are still available. The planet is still habitable. The civilization simply stops reproducing. Not because it cannot, but because it has decided, individually, generation by generation, that it would rather not. If this pattern is universal, and Dugan's argument is that it is a structural property of any species that gains voluntary control over its own fertility, then it explains the silence without invoking catastrophe. No nuclear war, no asteroid, no artificial intelligence turning hostile. Just a slow, quiet dissolution across every inhabited world in every galaxy that produced a technological civilization. Civilizations rise, develop technology, decouple reproduction from survival, and dissolve over a few hundred generations. The galaxy fills with ruins, and the ruins make no sound. 2 filters. Garrett's artificial intelligence window of roughly 200 years, Dugan's depopulation curve of 500 to 1,000 years, and both acting on civilizations that have reached our level, both potentially acting simultaneously on the same civilization, both describing processes already visible in human data, not as theoretical projections but as measured trends. For decades, the optimistic view held that the hard steps were behind us. The new evidence says otherwise. The filter may be ahead of us. And the data suggesting this comes not from exotic astrophysics, but from the birth statistics of every industrialized nation on Earth. There is a version of the Fermi paradox's resolution that does not involve death at all. It involves graduation. Seth Shostak at the SETI Institute has been making this argument for years in the face of the null results. Advanced civilizations are not louder than primitive ones. They are quieter. And a civilization 1,000 years ahead of us in technological development might communicate entirely through tight beam lasers, quantum encrypted channels, or technologies we have not yet conceived. Their communications would be invisible to us, not because they have gone silent, but because they have become efficient. And efficiency in communication naturally selects against the kind of leaky, omnidirectional broadcasting that makes a civilization detectable across light years. Think of it as the progression from a medieval town crier to a modern postal system. The town crier shouts the news in the public square. Everyone within earshot receives it. The modern postal system delivers information to specific addresses with far greater precision and far greater content. The information flow increased by orders of magnitude. The noise dropped to nothing. A civilization using tight beam communication could be exchanging more information in a single second than humanity has broadcast in its entire radio history, and we would detect nothing, because the signal is not aimed at us and is not leaking into space. The entire logic of SETI, of listening for electromagnetic leakage from technological civilizations, depends on catching them during a narrow window, advanced enough to produce detectable signals but not yet efficient enough to stop wasting them. That window might be 100 years. It might be 200. On a cosmic timeline of 13.6 billion years, 200 years is nothing. It is a camera shutter click. 2 civilizations would need to be in their leaky phase at the same time, within detection range of each other, or pointed at each other, producing signals we know how to recognize. The probability of that overlap drops with every decade that any given civilization becomes more efficient. The galaxy could be full of civilizations that graduated out of the detectable phase long ago, and we would have exactly the evidence we have, which is none. This is the most comfortable resolution to the paradox. It requires no catastrophe, no filter, no existential threat. It requires only that intelligence matures, and maturation reduces observable footprint. The problem with this resolution is that it requires additional assumptions that are themselves uncomfortable. A civilization that has survived for millions of years, that has mastered interstellar travel, or interstellar energy collection, should leave physical evidence. Not in its communications, but in its engineering. Stars managed differently. Stellar material moved. Entropy signatures inconsistent with natural processes. The Dyson sphere concept, proposed by Freeman Dyson in 1960, a shell or swarm of collectors built around a star to capture its entire energy output, would not be detectable by its radio emissions. It would be detectable by its infrared signature, the waste heat that thermodynamics guarantees no engineering can eliminate. In 2024, a project called Hephaestus published results that made international headlines. The team had scanned approximately 5 million stars within 1,000 light-years, looking for anomalous infrared excess that might indicate partial Dyson structures. 7M dwarf stars, the most common type in the galaxy, showed profiles that could not be easily explained by known astrophysical processes. The infrared excess was real. It was measured. It was consistent with what a partial stellar megastructure would produce. For a brief window, the scientific community allowed itself the thought. The follow-up analysis came in 2025. Independent teams re-examined the 7 candidates using additional data. What they found was not alien engineering. It was background contamination. The anomalous infrared signatures were real, but they were coming from objects billions of light-years behind the stars, dust-obscured galaxies and active galactic nuclei whose emissions had blended with the foreground starlight. Once higher-resolution data separated the background from the foreground, the megastructure signatures disappeared. The stars were ordinary, and the universe had, once again, perfectly mimicked the signature of advanced technology using nothing but random cosmic geometry and hot dust. A Dyson sphere search covering 5 million stars, the largest ever conducted, returned to zero. The universe is not just silent. It is actively deceptive. It produces phenomena that look engineered, that pass initial scrutiny, that survive preliminary analysis, and then collapse into mundane physics when examined more carefully. Pulsars in 1967, so regular they were labeled little green men before being identified as neutron stars. The wow signal in 1977, which passed every criterion for an artificial transmission and has never been fully explained, though the best current hypothesis is a rare natural phenomenon called a hydrogen master flare triggered by a magnetar, BLC-1 in 2020. And a narrowband signal from the direction of Proxima Centauri that survived months of analysis before being traced to electronics near the telescope itself. And now 7 stars that looked like partial Dyson spheres and turned out to be background galaxies. The universe keeps teaching us the same lesson. The absence of evidence is not evidence of absence. But after 5 million stars and 40 years of false positives, the weight of null results has accumulated past the point where it can be dismissed as a sampling problem. Not all proposed resolutions to the Fermi paradox are comfortable. Some are worse than the Great Filter. In 2008, the Chinese science fiction writer Liu Cixin published a novel called The Dark Forest, the second book in his 3-body problem trilogy. The book proposed an answer to the silence that was elegant, yet internally consistent, and deeply disturbing. It did not require that intelligent life is rare. It did not require that civilizations inevitably self-destruct. It required only that civilizations eventually learn the only rational strategy for survival in a universe of limited resources and uncertain intentions. The logic builds from 2 axioms. First, survival is the primary drive of every civilization. Second, civilizations continuously expand and require resources, but the total matter and energy in any region of the universe is finite. These 2 axioms create a situation that game theorists recognize immediately. A game with multiple players, finite resources, and asymmetric information, in which the optimal strategy is preemptive elimination of potential competitors. Here's why cooperation does not solve it. To cooperate, yes, you need to trust. To trust, you need to communicate. But communication reveals your location, and once your location is known, any sufficiently advanced civilization faces a choice. Deal with you now, while you are weak, or wait and face you later, when you might not be. A civilization that has survived long enough to master interstellar travel has survived in part by being ruthlessly rational about this calculation. It does not wait to find out whether you are friendly. It eliminates you before you become a threat. The universe in this model is a dark forest, packed with hunters. Every hunter knows the forest is full of other hunters. No one can see more than a few steps in any direction. Every sound, every signal, every emission of light or radio waves or infrared could attract a bullet. The rational strategy, the only strategy that produces long-term survival, is to stand perfectly still and eliminate any source of noise before it becomes large enough to threaten you. The observable prediction of the dark forest hypothesis is exactly the universe we observe. No signals, no megastructures, no expansion waves. A galaxy that looks, from the outside, precisely as it would look if every civilization that reached a sufficient level of capability had learned or been taught to go silent. The hypothesis has problems. It requires a level of paranoia that may not be universal. It requires that every civilization independently arrives at the same conclusion, with no exceptions, because one civilization that chose to broadcast would break the silence and we would have found it. And it assumes that destroying a distant civilization is cheaper than communicating with it. which may not be true across the energy scales involved in interstellar distances. And it assumes that the payoff from eliminating a competitor outweighs the cost of the operation, which depends on assumptions about resource scarcity that may not apply to civilizations with access to stellar-scale energy. But the hypothesis has one property that prevents complete dismissal. It is consistent with every observation. The silence is exactly what a dark forest universe would produce, and it cannot be falsified from inside the forest, because any attempt to look for evidence would itself be a survival risk. This is what makes it philosophically troubling in a way that most scientific hypotheses are not. Thus, it is not just a possible explanation for the paradox. If it is correct, the act of searching for extraterrestrial intelligence is the most dangerous thing our species has ever done. In 1999, a Russian astronomer named Alexander Zaitsev did something that no international body had approved and no scientific consensus had endorsed. He used the Yevpatoria planetary radar facility in Crimea, a dish originally built for deep space communication with Soviet probes, to transmit a high-powered, targeted message towards several nearby star systems. He called it Cosmic Call. The transmission was designed to be detectable by any civilization with a radio telescope comparable to our own. It contained mathematical and scientific information encoded in a format intended to be decipherable by any technologically capable species. And Zaitsev did not consult the SETI community before transmitting. He did not seek approval from any government. He did not need to, because there is no binding international protocol governing deliberate transmissions into space. None. The International Academy of Astronautics has guidelines. They are voluntary. No treaty, no law, no enforceable agreement prevents anyone with access to a sufficiently powerful transmitter from broadcasting a message into the cosmos right now, today, announcing humanity's existence and location to anyone who might be listening. The scientific community's response was immediate and divided. David Brin, who had written extensively about the Fermi paradox, called Zaitsev's action reckless. If the dark forest hypothesis carries even a small probability of being correct, and deliberately transmitting is the equivalent of lighting a bonfire in a forest full of predators. Brin resigned from SETI-affiliated committees in protest. Other researchers argued the opposite. Earth's military radar systems have been leaking detectable signals into space since the mid-20th century. Any civilization within 200 light-years that has the technology to threaten us already knows we are here. Hiding is pointless because we were never hidden. The debate has never been resolved because the underlying question is unanswerable. Is the universe dangerous or not? Science cannot say. What science can say is that the question has never mattered more than it does right now, at the moment when the search is becoming sensitive enough to begin approaching an answer, and when our own signals are becoming strong enough to begin attracting attention, if there is any attention to attract. Some resolutions to the Fermi paradox do not require that intelligent life is rare, or that it inevitably destroys itself, or that it hides out of fear. Some require only that it has decided, for reasons of its own, not to speak to us. The zoo hypothesis was proposed by John Ball in 1973. His argument was simple. Advanced civilizations might deliberately avoid contact with primitive species, the way a wildlife reserve keeps human visitors away from animals being studied. The animals in the reserve do not know they are being observed. They do not know the fence exists. They simply live in what appears to be a natural environment, unaware that their natural environment has been curated. Ball suggested that Earth might be such a preserve, that the silence is not cosmic but deliberately maintained, that we are living inside a managed silence we mistake for universal emptiness. The zoo hypothesis is difficult to take seriously in its strong form because it requires all civilizations in the galaxy to agree on the same policy, with no defectors. One civilization that disagreed with the no-contact rule would break the silence. The probability that every civilization throughout the galaxy's history arrived at the same conclusion and enforced it without exception is not zero, but it approaches it. The planetarium hypothesis, proposed in fiction by Stephen Baxter in 2001, takes the zoo idea to its logical extreme. If a sufficiently advanced civilization wanted to keep a primitive species from detecting its existence, if the most thorough method would not be to avoid transmitting, it would be to control what the primitive species observes A civilization capable of building structures around stars, capable of engineering on planetary or stellar scales, might be capable of projecting a false cosmology inward from the boundary of our observable universe. What we see when we look at the night sky, every galaxy Webb has cataloged, every measurement we have made of cosmic structure could be a constructed display, designed to show us a universe that appears empty. The planetarium hypothesis is scientifically useless because it is unfalsifiable. There is no observation you could make that would distinguish a genuine empty cosmos from a constructed one, because any evidence of the simulation could itself be part of the simulation. Yet it sits entirely outside the reach of the scientific method, but it is logically consistent with everything we observe. Nothing in the known laws of physics prevents a sufficiently advanced civilization from doing this. The energy requirements would be enormous, roughly equivalent to capturing the entire output of a star, which is precisely what a Dyson sphere is designed to do. What these ideas expose is a limit in the epistemological framework of the search. Every explanation for the silence that has been proposed assumes we are seeing the actual universe. If that assumption is wrong, even partially, every conclusion built on top of it is vulnerable. The resolution to the paradox might not be a fact about the universe, but a fact about who controls what we are allowed to see of it. This is not a comfortable place to end up. And it is the kind of thought that responsible scientists set aside because it produces no testable predictions. But the Fermi paradox has a way of leading you to uncomfortable places if you follow the logic honestly. At its edges, the paradox touches questions that science is not equipped to answer definitively. Questions about the structure of reality and who, if anyone, is managing it. Most working scientists decline to go that far. They prefer to stay within the domain of things that can in principle be tested. But the domain of things that can be tested has so far produced a single result, and that result is the same as the one Enrico Fermi encountered over lunch in 1950. Nothing. There is a category of proposed resolution that requires neither death nor deliberate hiding. It requires only that intelligence, having solved the problems of survival that drove its evolution, discovers that the interesting universe is not the one outside. The simulation hypothesis in its benign form, not the paranoid version but the philosophical one, suggests that sufficiently advanced civilizations would spend most of their computational resources running detailed simulations of possible worlds rather than exploring physical space. If a civilization can simulate minds and realities indistinguishable from the physical variety, the motivation to expand into physical space diminishes. Why travel light years to experience a new environment when you can construct 10,000 environments richer than anything nature provides and experience them at any speed you choose? The technological path that leads to this outcome is already visible in embryonic form. Virtual reality, increasingly immersive and increasingly capable of substituting for physical experience. Social media and digital communication, which have already begun to substitute for physical proximity in ways that affect where people choose to live and work. Artificial intelligence, which is demonstrably capable of generating experiences indistinguishable from human-produced ones in many domains. The trajectory is clear. The question is not whether this technology will be developed, but how far it will develop and what it will do to the relationship between intelligence and physical space. A civilization that retreats into simulated experience leaves behind exactly the evidence we observe. None. No signals, because internal experience requires no external transmission. No megastructures, because physical expansion is not the goal. No expansion fronts, because the civilization is not expanding, it is intensifying. A related idea is sometimes called the transcension hypothesis, proposed by John Smart. The argument is that advanced civilizations do not expand outward into physical space, but inward, into increasingly efficient computational substrate at smaller and smaller scales. The motivation is thermodynamic. The most efficient computation happens at high density and low temperature, not spread across light years of space. A civilization optimizing for computational efficiency would not build megastructures around stars. It would build dense, compact, energy-efficient systems at microscopic scales, invisible from any distance. There is also the estivation hypothesis proposed by Anders Sandberg, Stuart Armstrong, and Milan Cirkovic. Their argument is cosmological. The universe is currently too hot for maximally efficient computation. As the universe expands and cools over the next tens of billions of years, the available computational efficiency increases. A civilization that wants to maximize the total amount of computation it can perform over its entire history would not spend its energy now, when it is expensive. It would store its energy, shut down most of its operations, and wait. Aestivating, like an animal in summer torpor, conserving resources until conditions improve. A galaxy full of estivating civilizations would look exactly like the galaxy we observe. Silent, dark, apparently empty. Not because life is rare or civilizations are fragile, but because the rational strategy for a civilization optimizing over cosmic timescales is to wait for a universe that is better suited to what it wants to do. These hypotheses share a common feature that makes them simultaneously compelling and frustrating. They all produce the same observable prediction, which is the observation we already have. They are consistent with the data but cannot be distinguished from each other, or from the null hypothesis that intelligent life is simply rare, by any measurement we currently know how to make. What they collectively suggest is something worth sitting with. The silence we observe might not be the silence of a universe that failed to produce intelligence. It might be the silence of a universe in which intelligence, having emerged, consistently discovers that the external cosmos is less interesting than what it can build inside. That possibility changes the character of the Fermi paradox. It stops being a mystery about absence and becomes a question about priorities. Not where is everybody, but where did everybody go? And the answer in this reading is inside. In early 2026, the state of the question looks like this. The galaxy is old enough to have produced technological civilizations billions of years before us. The universe produced the chemical conditions for rocky planets with heavy element enrichment within the first billion years after the Big Bang. The origin of life appears to be relatively easy, robust enough to begin almost as soon as conditions allowed on Earth. The emergence of intelligence is rarer, at requiring specific geological and ecological conditions sustained over long time scales, but not so rare as to make our existence miraculous, rather than statistically predictable. Somewhere between the emergence of intelligence and the detectable civilization, something happens that produces the silence we observe. The new answer, insofar as a new answer exists in early 2026, is not a single resolution, but a convergence of probabilities. The intelligence bottleneck is real. Stern and Garrier's analysis suggests that the fraction of life-bearing planets that develop intelligence capable of technology is small enough to explain significant scarcity on its own. Not near universal scarcity, but significant scarcity. This does not fully resolve the paradox. And a small fraction of 40 billion habitable planets in the Milky Way is still millions of worlds. But it narrows the expected population from millions of active civilizations to thousands or fewer. The detection window is real. Garrett's analysis of the AI timeline, even if the specific number of 200 years is debated, captures something genuine about the trajectory of technological civilizations. The phase during which a civilization leaks detectable signals while remaining the kind of thing that produces them is short. Very short relative to geological time. The probability that two civilizations would be in their leaky phases simultaneously within detection range of each other is genuinely low, even if civilizations are not rare. The demographic transition is real. Dugan's analysis draws on measured trends, and not theoretical models. The fertility rates of industrialized nations are below replacement and declining further. The trend appears structural rather than cyclical, resistant to policy intervention at the scale governments can manage. If this pattern is a universal property of species that gain voluntary control over reproduction, it limits the duration of any civilization's detectable and expansive phase from the other end. Put these together, and the picture that emerges is not the great filter as a single dramatic barrier. It is a gauntlet. Multiple filters, each one attenuating the probability of a detectable civilization from the population of potentially habitable worlds. The intelligence bottleneck thins the initial population. The detection window limits the observable duration, yet the demographic transition constrains the maximum duration. And within that remaining population and that narrow window, you still have to be looking in the right direction at the right time with the right instruments. The new answer is probably both. The filter is partly behind us, in the genuine difficulty of producing intelligence and technology from biology, and partly ahead, in the difficulty of surviving the transition to mature technology long enough to become the kind of civilization that leaves a visible mark on the galaxy. This is not a satisfying answer. It does not resolve the paradox into a clean conclusion. It distributes the probability across multiple mechanisms, each one real, each one partial, none one sufficient alone to explain the full depth of the silence. But it is more honest than any single explanation, and it is more consistent with the accumulated weight of evidence from every domain that has bearing on the question. The paradox does not go away. It becomes more articulate. Before accepting any resolution too quickly, it is worth examining the most stubborn piece of evidence that the silence might not be as complete as it appears. On August 15th, 1977, a volunteer astronomer named Jerry Eman was reviewing data printouts from Ohio State University's Big Ear radio telescope. Big Ear was a flat reflector telescope that scanned strips of sky as Earth rotated. The data came out on continuous paper, columns of alphanumeric characters representing signal intensity at different frequencies. One sequence jumped off the page at exactly 1,420.726 MHz, the hydrogen line, and a signal appeared that was roughly 30 times louder than the background noise of space. The peak intensity exceeded 250 Janskys. It lasted 72 seconds, which was exactly how long a celestial source would remain in Big Ear's beam as Earth turned. The signal behaved precisely the way an extraterrestrial transmission should behave. It arrived at the frequency that would be the obvious choice for any civilization trying to communicate. It came from a fixed point in the sky rather than tracking with local interference. It peaked, held, and faded in exactly the pattern of a cosmic source transiting the beam. Eman circled the character sequence and wrote a single word in red ink in the margin. Wow. The signal never repeated. Eman and others pointed Big Ear at the same coordinates hundreds of times over the following years. Nothing. Other telescopes searched the same sky. Nothing. The signal came from the direction of the constellation Sagittarius, from a region with no remarkable star or known object. For 40 years, the WOW signal sat as the single strongest candidate for an extraterrestrial transmission in the history of the search. Every proposed natural explanation failed to account for either the frequency precision or the intensity. Then in 2017, an astronomer named Antonio Paris proposed that 2 comets had been in the general area of Big Ear's beam on that night, and that their hydrogen envelopes could have produced the signal. Several media outlets reported the mystery as solved, except it was not. Critics pointed out that the comets were not in the correct beam position on that date. More fundamentally, comets emit at 1,420 MHz at extremely low power. The emission a hydrogen cloud around a small comet can produce is many orders of magnitude weaker than 250 Janskys. Proposing a comet as the source of the WOW signal is like proposing a candle as the cause of a forest fire visible from orbit. The scale is wrong by a factor that cannot be absorbed by any reasonable uncertainty in the estimates. In 2025, a team decided to go back to the original data, 75,000 pages of dot matrix printouts from Big Ear's observation run in August 1977, sitting in archives for nearly half a century. They digitized the entire dataset using optical character recognition and conducted a full systematic reanalysis. The results confirmed what Eman had seen, but with greater precision. The WOW signal's flux density exceeded 250 Janskys. As the comet hypothesis was definitively eliminated, the positional analysis confirmed that neither candidate comet was in the correct feed horn beam on that date. The new best hypothesis is something nobody had anticipated. Researchers now propose that the WOW signal was a rare superradiance event, possibly triggered by a magnetar, a neutron star with an exceptionally powerful magnetic field passing near or through a cloud of cold hydrogen gas. Under specific and unusual conditions, such a cloud can be stimulated to emit a sudden, intense burst of radiation at exactly 1,420 megahertz. The emission is coherent, brief, powerful, and non-repeating. This explanation fits every observed characteristic of the signal. The WOW signal was not intelligence, but it was also not comets. It was something the universe produced through raw physics. It is so rarely and so precisely that it mimicked an artificial transmission at the exact frequency we were monitoring on the exact night someone was watching. The universe is actively deceptive. It produces phenomena that look engineered, that pass every filter, that survive initial scrutiny, and then reveal themselves as natural processes so unusual that no one had predicted them. The pattern is consistent across 6 decades of searching. Pulsars in 1967, the WOW signal in 1977, BL-C1 in 2020, 7 Dyson sphere candidates in 2024, dimethyl sulfide on K2-18b in 2023. Each one looked, for a moment, like the answer. Each one resolved into physics or instrumentation. The universe has not confirmed the silence by being quiet. It has confirmed it by producing false positives so convincing that the most sophisticated instruments and most rigorous analysts the species has produced have repeatedly held their breath, checked the data, checked it again, and slowly exhaled. The silence is not peaceful. It is the most carefully examined silence in the history of science. There is a version of the Fermi paradox that is not about death or hiding or efficiency. It is about perception. We might be missing everything. Jill Tarter, who spent 35 years directing the search for extraterrestrial intelligence and was the real-world inspiration for the protagonist of the film Contact, made this argument for decades. She put it in terms of ocean sampling. Imagine you want to know if there are fish in the ocean. You walk to the shore, scoop up a single hot tub of water, look inside, find nothing, and conclude the ocean is empty. That would be absurd. And yet, she argued, that is roughly what SETI has done. All of our searching, every dish pointed at every star, every frequency scanned, every algorithm run, amounts to an infinitesimally small sample of the possible detection space. The argument was compelling for decades because it was true. Less than 1% of the sky had been searched at the frequencies and sensitivities that matter. Earth's radio bubble, the sphere of electromagnetic signals that has leaked outward from our planet, covers roughly 15,000 stars. The Milky Way contains somewhere between 200 billion and 400 billion stars. We are invisible to 99.9999% of the galaxy. The hot tub analogy was not rhetoric, it was accurate arithmetic. But the argument has weakened as the searches have grown. The Breakthrough Listen program scanned approximately 1 million nearby stars and accumulated more than 2 petabytes of data. The Commensal search on the Very Large Array covered 950,000 unique fields in under a year. The Murchison Wide Field Array surveyed 2,800 entire galaxies. The FAST telescope in China, the largest single-dish radio telescope ever built, is currently re-examining approximately 100 candidate signals that survived 21 years of SETI at home processing and have not yet been explained away. At some point, the ocean argument stops working. Not because we have searched the whole ocean, we have not, but because we have sampled enough distinct regions with enough different methods and across enough different frequency ranges over enough elapsed time that the null result is no longer consistent with a uniform distribution of detectable civilizations. If technological civilizations were common, broadcasting at any reasonable rate across the range of frequencies we have searched, we would have detected something by now. The statistical models built on the accumulated null results constrain the number of detectable civilizations in the Milky Way to fewer than 1 to 5 per century. That number came from the data. It is not a theoretical claim, but the sampling argument has a version that is harder to dismiss. We are searching for signals we know how to detect. Radio waves. infrared excess, narrowband transmissions. These are the technologies of the 20th century. A civilization 1,000 years ahead of us in development would not necessarily use any of them. They might communicate through modulated neutrino beams, which would pass through Earth undetected by any instrument we possess. They might use quantum-entangled communication, which cannot be intercepted by conventional radio telescopes. They might use gravitational wave modulation, or dark matter interactions, or technologies that operate in domains of physics we have not yet discovered. The assumption underlying every SETI search is that intelligent civilizations would communicate in ways we can recognize. That assumption may be deeply wrong. We are looking for our reflection in a mirror that might not reflect the kind of light that other minds emit. The silence could be the silence of a language we do not have the organs to hear. As there is also the question of what we would recognize as evidence of intelligence. The megastructure searches assume that a civilization sufficiently advanced to modify its star system would produce modifications we could detect from stellar distances, but the 7 Dyson sphere candidates in 2024 were identified by specific infrared signatures. If a more advanced civilization built megastructures that were thermodynamically efficient enough that the waste heat was below our detection threshold, or distributed the heat in ways that mimicked natural stellar processes, we would not find them. The universe might be full of engineering we cannot distinguish from nature because the engineers are better at thermodynamic management than we assumed. The new answer to the Fermi paradox must account for this, not as a cop-out that explains away the null result, but as a genuine constraint on what the null result proves. We have searched for what we know how to look for. We have found nothing. What that proves depends entirely on whether what we looked for is what is there to find. Think about what it means to look at something far away. The moment you see a distant object, the light reaching your eyes left that place some time ago. This is one of the most profound facts in all of science, and the James Webb Space Telescope has turned it into the most powerful archaeological tool humanity has ever built. When you look at the moon on a clear night, you see it as it appeared about 1 1/3 seconds ago. A small delay, nearly invisible. But stretch that distance and the delay transforms into something breathtaking. At the nearest star beyond our own, a red dwarf called Proxima Centauri sits 4.2 light-years away. The light from it that reaches Earth tonight completed a 4-year crossing of nearly perfect emptiness to get here. During those 4 years, entire political cycles ran their course. Go further. The Andromeda Galaxy hangs in the northern sky as a faint smear visible to the naked eye on a clear night. The light that falls on your retina from it tonight left its source 2.5 million years ago. At that moment, our ancestors were chipping rocks into tools on the African plains. They had no concept of galaxies, telescopes, or the void they lived inside. That ancient light has been crossing space ever since. It did not wait for us to exist. It simply arrived. Now consider a photon from MOM Z14, and the galaxy confirmed by the Yale team in May 2025 at the highest redshift ever spectroscopically verified. That photon traveled for 13.5 billion years before James Webb intercepted it. When the telescope decoded that signal into data, it was capturing a galaxy as it appeared when the universe was 280 million years old. Our solar system did not yet exist. The atoms in every human body had not yet been forged inside any stellar furnace. The Milky Way itself was still assembling its first structures in the dark. Now extend that same thinking to the Fermi paradox. If a civilization existed in a galaxy like MOM Z14 13 billion years ago, and if that civilization ever transmitted detectable signals, those signals have been crossing space ever since. They are out there now, spreading through the cosmos at the speed of light, diluting with distance but still traveling. The question of whether we could detect them is different from the question of whether they exist. A signal transmitted from a galaxy 13 billion light-years away at radio frequencies would be redshifted far out of the range our instruments cover, and would be diluted by the square of that distance to intensities below any threshold we can reach. But a signal transmitted from within our own galaxy, by a civilization that existed 1 billion years ago, might still be detectable by instruments more sensitive than the ones we have. This is the temporal dimension of the search that is rarely discussed. We are not just searching space. We are searching time. The signals we could detect are not just the signals being transmitted now, yet they are the echoes of transmissions that might have been sent 1 billion years ago, still propagating through the galaxy in all directions. A galaxy-spanning search, sensitive enough to pick up those echoes, has not yet been built. The universe is also telling us something about what happened to the early civilizations that might have arisen in the first 1 billion years after the Big Bang. The galaxy's web is finding from that era are compact, intensely star-forming, chemically enriched beyond what models predicted. They are building the heavy elements at a furious rate. They are, in principle, building the substrate for rocky planets, for oceans, for chemistry, for life. But the universe in those first 1 billion years was also very different from the universe today. It was denser. The cosmic microwave background radiation, yet the afterglow of the Big Bang, would have bathed every surface in the universe with a temperature that was not much cooler than today's average planetary surface temperature. The thermal environment of the early universe might have been hostile to the kind of stable, long-lived chemistry that life requires, even on planets orbiting stable stars. The early universe might have been the wrong kind of place for the kind of life we are looking for. Which means the civilizations that Webb's data suggests could have existed might not have existed in the form that would produce the signals we are searching for. Or they existed and evolved and resolved the Fermi paradox from their own perspective in ways we cannot imagine. And the resolution they found is the same resolution every civilization before us has found. And we are next. Every explanation for the Fermi paradox has something in common beyond its content. It says something about us. The argument that the filter is behind us, in the rare emergence of complex life and intelligence, is the argument of species that is proud of what it achieved and wants to believe the hard part is done. It is the argument of survivor bias, elevated to cosmology. We made it through. We are the exception. The rest of the universe failed at the steps we cleared. The argument that the filter is ahead of us in the self-destruction that awaits any civilization that reaches our level is the argument of a species that can see its own vulnerabilities, nuclear arsenals, climate systems under pressure, artificial intelligence developing faster than the ethical frameworks to govern it. The demographic collapse already visible in birth statistics. These are not hypothetical threats. They are present and measurable. The argument that they will eventually consume every civilization is not pessimism for its own sake. It is pattern recognition applied to the only data point we have. The dark forest hypothesis is the argument of a civilization that has studied its own history and found it full of conquest and preemptive violence and the elimination of perceived threats before they became actual ones. It projects that pattern onto the cosmos. It imagines the universe as a scaled-up version of human strategic behavior. Whether that projection is accurate is unknowable. Whether it is revealing about the mind that produced it is not. The simulation hypothesis, the transcension hypothesis, the estivation hypothesis, is the idea that advanced intelligence turns inward rather than outward. These are the arguments of a species that is beginning to suspect that the most interesting things in the universe might not be outside it. They are the arguments of a civilization that has begun to produce virtual realities and artificial minds and experiences richer than nature provides unaided. And that is starting to wonder whether the extraterrestrial silence might be the sound of every civilization that got there first, discovering the same thing. The Fermi paradox is not just a question about aliens. It is a question that holds a mirror up to whoever is asking it. The answer a civilization produces says something about where it is in its own trajectory. Early civilizations ask, "Are we alone?" Middle civilizations ask, "Where did everyone go?" Late civilizations may not ask at all because the question has answered itself. We are asking because we are early enough that the silence is still surprising, early enough that we have not yet resolved it from the inside, early enough that the question still feels urgent rather than settled by experience. That may be the most important thing the Fermi paradox tells us, not about the universe, about ourselves. In 2016, Christopher Consolis at the University of Nottingham published a revised estimate of the total number of galaxies in the observable universe. The previous figure, which had sat in textbooks for 2 decades, was somewhere between 100 billion and 200 billion galaxies. The origin of that estimate was straightforward. Count the galaxies visible in a small patch of sky from the Hubble Space Telescope's deep field images, extrapolate to the full sky, arrive at a large number. Consolise's team recognized that the straightforward extrapolation was missing something essential. The most distant, faintest galaxies in the early universe, the small, numerous objects that dominated the first billion years of cosmic history, were simply below the detection threshold of every telescope that had existed. They were real. They were out there. But they had never been counted. The corrected total was closer to 2 trillion galaxies. 2 trillion separate island universes, each containing hundreds of billions of stars, each star potentially hosting planets, each planet potentially hosting life. More than 90% of all galaxies in the observable universe had been invisible to human instruments, and therefore absent from every count ever made. 2 trillion. Consolise offered a comparison to give the number a human scale. 2 trillion is roughly the number of seconds in 1,000 average human lifetimes. Counting at 1 galaxy per second, without pause, without sleep, would take 63,000 years to reach 2 trillion. Human civilization, including all of recorded history from the earliest writing to the present day, is approximately 10,000 years old. The count would not be finished in the entire span of human civilization so far, 6 times over. The James Webb Space Telescope's Cosmos Web Survey, which cataloged nearly 800,000 galaxies in a patch of sky 3 times the size of the full moon, represents a step toward mapping that population. Extrapolate the galaxy density visible in that patch across the full sky, and you approach the 2 trillion estimate from the data, rather than from a model. 2 trillion galaxies, each one containing hundreds of billions of stars, each star potentially hosting planets. At a conservative estimate of 1 potentially habitable world per 5 stars, the number of candidate planets in the observable universe reaches into the hundreds of millions of trillions. 2 times 10 to the 23rd power. 20 trillion worlds where the chemistry of life might in principle have found purchase. And we have found, in all of that, exactly 1 world where it demonstrably has. And the scale of the number on one side and the scale of the number on the other are the Fermi paradox in its most distilled form. Not where is everybody, but how, given 2 trillion galaxies and 20 trillion candidate worlds and 13.8 billion years, is it possible that we find ourselves apparently alone in a universe this vast? The new answer must account for this. The intelligence bottleneck, the detection window, the demographic transition. These are filters operating on the population of a single galaxy. They narrow the expected number of detectable civilizations from thousands to tens or fewer. They do not address the 2 trillion galaxy problem. Even if every galaxy in the observable universe had only a single technological civilization in its entire history, there should be 2 trillion civilizations, and almost all of them older than us, almost all of them with more time to develop and expand and make themselves visible. Unless the filters are not additive, unless they compound, unless each one is not reducing the expected population by an order of magnitude, but by many orders of magnitude, unless the combination of the intelligence bottleneck and the AI window and the demographic collapse and the dark forest and the transcension and the efficiency silence, all acting independently on every civilization that reaches a certain level, produces not thousands of detectable civilizations per galaxy, but 1 per galaxy, or fewer. 1 per 2 trillion galaxies. 1 per observable universe. 1 per history. Us. In the mountains of Guizhou Province in southwestern China, and a natural limestone depression holds the largest single-dish radio telescope ever constructed. The 500-meter aperture spherical telescope, known as FAST, stretches 500 meters from edge to edge. If placed in downtown Manhattan, it would cover the distance from Wall Street to City Hall. Since the collapse of the Arecibo Observatory on December 1st, 2020, FAST has been the most sensitive radio ear humanity has ever built. Since July 2025, FAST has been working through a specific list. When the SETI at Home Distributed Computing Project shut down in March 2020, after 21 years of operation, it left a legacy. Out of 12 billion candidate signals processed by volunteer computers worldwide, approximately 100 survived every stage of automated filtering. Yet these were the signals that software could not classify as terrestrial interference, satellite contamination, or instrumental artifacts. They were anomalous enough that human researchers flagged them for follow-up with a more powerful instrument. FAST is that instrument. It is re-observing each candidate one by one, pointing its dish at the same celestial coordinates, tuning to the same frequencies, listening for any signal that repeats or matches the original detection profile. The process is methodical. Each target receives multiple observation sessions at different times to account for the possibility that a signal might be intermittent or directional. As of early 2026, FAST has reported nothing from any of the re-observed candidates. Yet the 100 signals that survived 21 years of distributed computing and billions of hours of volunteer processing are dissolving one by one under the scrutiny of a better telescope. They are not resolving into alien transmissions. They are resolving into the same category everything else resolves into: noise, instrumentation, natural processes we had not accounted for. Meanwhile, machine learning algorithms developed for breakthrough listen now process radio telescope data 600 times faster than conventional methods. A dataset that would have taken a human team years to analyze can be filtered in days. The volume of sky being systematically searched per unit of time is growing exponentially compared to 5 years ago. The Allen Telescope Array is being upgraded, and new commensal systems are being installed on radio telescopes across 4 continents. The search has never been faster, broader, or more sensitive. The result has not changed. The number at the end of every pipeline remains the same number it was in 1960, when Frank Drake pointed an 85-foot dish at 2 stars and heard nothing. It was 0 then. It was 0 after 1 million breakthrough listen stars. It was 0 after 950,000 commensal fields and 74 million narrowband hits from an interstellar visitor that passed through our solar system in July 2025. 3. I/Atlas, the third confirmed interstellar object to pass through our solar system, was detected as it approached in 2025. The Allen Telescope Array pointed at it within days, over 7.25 hours of observation, as the array recorded 74 million narrowband signals. Automated filters reduced that to 211 candidates worth closer examination, every single one traced to terrestrial origin. An object that came from another star system passed through our solar system while we watched, and it carried nothing. Or it carried everything it carried in a form we cannot read, which is the same as nothing from where we stand. The search is not going to stop. FAST is still listening. Breakthrough. Listen is still accumulating data. New instruments are coming. The question is not whether the search will continue. The question is what it means at this point in its history that it has found nothing. The hot tub argument, the argument that we have barely sampled the ocean, was sufficient to hold the question open for the first 40 years of formal searching. The accumulated weight of modern null results has made it harder to maintain that position without qualification. 6 decades, 12 billion processed candidates, 74 million narrowband hits from an interstellar visitor, not one confirmed signal of artificial origin. At some point, the absence of evidence becomes evidence of absence. That point is not a bright line. It is a gradual shift in what the data can and cannot sustain. We crossed it some time ago. The Fermi paradox is not waiting to be answered by a better telescope. The Fermi paradox is telling us something now, with the telescopes we have, and the something it is telling us is not comfortable. Yet the crisis in cosmology that James Webb has generated is not separate from the Fermi paradox. It is the same crisis, viewed from a different angle. When the James Webb Space Telescope found oxygen in a galaxy that existed 290 million years after the Big Bang, published simultaneously by 2 independent research teams in early 2025, the reaction from both groups was the same. The oxygen should not have been there. The standard models predicted chemical enrichment at this level would require multiple complete cycles of stellar birth and death, cycles that take millions of years per generation, cycles that had not had time to complete in the 290 million years the galaxy had existed. One team leader described the finding as discovering an adolescent where you would only expect babies. The galaxy was already chemically mature in an infant universe. What this means for the Fermi paradox is that the universe was seeding the raw materials for rocky planets and complex chemistry much earlier than anyone had modeled. If rocky planets with oxygen atmospheres could form within the first few 100 million years after the Big Bang, the first civilizations might have arisen not a few billion years before us, but 10 or 12 billion years before us. A civilization that arose 12 billion years ago in a galaxy in the earliest epoch of the universe would have had 12 billion years to develop, to expand, to send signals, to leave marks. 12 billion years is enough time to visit every star in the Milky Way at a fraction of a percent of light speed in return. It is enough time to dismantle a star, build a Dyson sphere, and run the waste heat up to levels detectable across intergalactic distances. It is enough time to do anything that physics allows. The silence that confronts us is not just the silence of a galaxy that has been around for 13 billion years. It is the silence of a universe that has been building the conditions for life for most of its history, and yet shows no evidence, at any scale, at any frequency, in any form we have looked for, of having produced anything that lasted. Or it shows no such evidence to instruments and methods that are 100 years old, searching a fraction of a percent of the observable universe, for signals in a few frequency bands out of the continuous spectrum of possible communication channels. Both things are true at the same time. The null result is significant, the search is incomplete. So these are not contradictory facts, they are the two sides of a measurement that has not yet converged on a final value, and the final value will determine something more important than whether aliens exist. It will determine whether we do, in any form that future generations would recognize as what we are now. Stand outside on a clear night, not in a city where the light pollution washes out everything but the moon and a handful of the brightest stars. Somewhere dark, somewhere where the Milky Way is visible as a band of light across the sky, not as a concept, but as something you can see with unaided eyes. Look at it for a few minutes, long enough to begin to feel the scale of it. What you are seeing is approximately 100 to 400 billion stars. The distance from edge to edge is roughly 100,000 light years. Every star in that band is potentially a sun with planets. Many of them are suns with planets. Statistically, a significant fraction of those planets are rocky. A fraction of those rocky planets are in orbits where liquid water is possible. In the Milky Way alone, the estimate is 40 billion such worlds. Now consider what the Fermi paradox is telling you about those 40 billion worlds. Not that they are barren. Not necessarily. The origin of life appears to be something the universe does readily in the right conditions. Microbial life may be common, distributed across millions or billions of worlds throughout the galaxy, a thin biological layer on rock after rock in the darkness between stars. What appears to be absent is not life. What appears to be absent is the life that looks back, the life that builds telescopes, that asks where everyone is, that develops technology capable of modifying its environment on a civilizational scale. That form of life, if it exists elsewhere in the galaxy, has not made itself known in a way that 6 decades of increasingly sensitive searching has been able to detect. The Great Filter is the name for whatever stands between the microbial life that the universe seems to produce readily and the technological civilization that the universe seems to produce rarely. It might be the emergence of the eukaryotic cell, a step that took 2 billion years on Earth and might have been extraordinary luck. It might be the development of intelligence itself, constrained to the fraction of life-bearing worlds that sustain the specific geological conditions Stern and Jerry identified. And it might be the survival of technological civilizations past the point where they develop the tools to destroy themselves. The new answer, the answer that the accumulated evidence of 2024 and 2025 and early 2026 is pointing toward, is that the filter is not a single thing. It is the combination of all the attenuating factors working together. The intelligence bottleneck is real, but not sufficient alone. The detection window is real, but not sufficient alone. The demographic transition is real, but not sufficient alone. Together, along with some contribution from the dark forest or the transcension, or the simple fact that we are probably early in the universe's civilizational timeline, they reduce the expected population of currently detectable technological civilizations to a number consistent with zero observed. The resolution does not require a dramatic single catastrophe. It requires a cascade of filters, each one removing a fraction of the potential population, their combined effect, producing a galaxy that looks to our instruments precisely as the galaxy we observe. What this means for our future is the question the paradox was always building toward. If the filter is behind us, we pass the hardest steps. We are here, which means we made it through whatever nearly everyone else did not. The silence is the silence of a galaxy that mostly failed before it reached us. We are the rare success. The hard part is done. If the filter is ahead of us, we are inside the danger zone right now. The AI timeline, the demographic collapse, the political instability that advanced weaponry and resource competition can produce. These are not hypothetical. They are present. They are the exact pressures that the Garrett and Dugan models describe as civilizational killers. We have built the instruments. We have not yet determined whether we will be the next null result. The Fermi paradox does not give us a comfortable answer. What it gives us is a measurement of our situation. It tells us that civilizations like ours are rare or brief, or both. It tells us that making it to the next stage of the journey is not guaranteed. It tells us that the universe has had billions of years to produce examples of what comes after us. And the evidence for what comes after us, whatever that is not visible from here. Whether that is because the silence is a mirror of what awaits us, or because what comes after us is simply too advanced and too quiet for us to see. It is the question that defines the difference between a civilizational horizon and a civilizational ceiling. We do not yet know which one we are approaching. There is one more hypothesis that deserves space here, not because it is the most scientifically rigorous, but because it is the most personally affecting. The idea that we might be early. The universe is 13.8 billion years old. The stars capable of supporting long-lived planetary systems around them, sun-like stars, will continue forming for roughly another 5 trillion years. That is 360 times the current age of the universe remaining. The stelliferous era of the cosmos, the era in which stars burn and the conditions for life as we know it persist, has barely begun. If intelligent life continues to emerge throughout that vast future era, then the civilizations that exist today, including ours, are among the earliest in the universe's history. Not the first, because rocky planets with heavy element enrichment were forming billions of years before Earth. And the conditions for life may have been met in some of those early systems. But early. Early enough that the kind of communication we have been listening for, the kind that implies civilizations that have been around long enough to spread through their galaxy and develop technologies we might recognize, is rare. Not because civilizations inevitably fail, but because the universe has not yet had time to produce them in abundance. In this reading, the Fermi paradox is not a paradox at all. It is the natural condition of any civilization that arises before the peak of the universe's civilizational productivity. As we are looking out at a universe that is only in the early stages of the process that will eventually fill it with mind, the silence is not permanent, it is present. David Kipping at Columbia University has done calculations on this. If you ask what fraction of all observers who will ever exist in the observable universe are alive today, the answer is very small. Not because there are many of them now, but because there will be so many more of them later. Most minds that will ever exist will arise in a universe far older than ours, around stars far dimmer and longer lived than our sun, on timescales we cannot intuitively process. We might be the first chapter of a story that will continue for trillions of years. We are asking where everyone is, and the answer might be, they have not been born yet. The universe has not finished making them. We arrived early, before the party started. And the silence we hear is not the silence of absence. It is the silence of anticipation. This does not mean the other filters do not operate. The intelligence bottleneck is real regardless of when it operates. The detection window is real regardless of how many civilizations will eventually arise. But it adds a temporal dimension to the paradox that is easy to miss when you are focused on the galaxies that already exist. The observable universe contains 2 trillion galaxies. What it will contain in 1 trillion years, after the current generation of stars has burned out, and the next generation has formed and the conditions for life have propagated through every nook and cranny of the universe, is a different question. And the Fermi paradox, as we experience it, is the Fermi paradox of a young universe. The answer to it may be a function of our timing rather than our uniqueness. Before the wonder calcifies into certainty, a pause. Science advances through challenge, and the Fermi paradox is no exception. Everything that has been laid out here, the intelligence bottleneck, the AI filter, the demographic transition, the dark forest, the transcension, the early observer hypothesis, all of it is provisional. These are the best current interpretations of the available data. The data itself is incomplete. The interpretations are contested. The history of the field is a history of confident conclusions later revised. The 2 trillion galaxy estimate is a projection. Christopher Consolus's 3-dimensional modeling of galaxy density across cosmic time is sophisticated and well regarded, but it is still a model, not a direct count. The actual number could be higher. It could be somewhat lower if assumptions about faint galaxy formation turn out to need revision. The impossible galaxies problem is real. The gap between what the standard cosmological model predicted and what Webb has found at extreme redshifts is large and persistent. But most working cosmologists are not ready to declare the standard model broken. The leading interpretation is that the early universe formed stars faster than models assumed, which requires significant adjustment, but may not require a new framework. The Stern and Jarier estimate of intelligence frequency is a calculation with significant uncertainty at every step. The geological requirements they identify are real, but the degree to which they constrain the probability of intelligence is not established with the precision they claim. The fossil record of Earth provides one data point. Extrapolating from one data point to a universal frequency is an exercise in motivated reasoning as much as genuine inference. The AI filter model rests on the assumption that 127 years is a representative window between first radio transmission and advanced artificial intelligence. That assumption is based on exactly one civilization, ours, at one point in its development. Projecting it as a universal property of technological civilizations requires the assumption that the pressures driving AI development are universal, which may be true but is not established. Most importantly, the sample size for the Fermi paradox for the question of how common technological civilizations are and what happens to them is 1. We know life exists on Earth. We know of no confirmed life anywhere else. Drawing statistical conclusions about the probability of intelligence across 2 trillion galaxies from a single example is epistemologically precarious, however compelling the logic seems. The honest scientific position is not that we are alone and not that we are not. It is that we do not know, and the tools capable of beginning to find out are only now coming online. The Euclid telescope, launched in 2023, is mapping large-scale structure at scales Webb cannot cover. The Nancy Grace Roman Space Telescope will survey areas far larger than Webb's deepest fields. Ground-based observatories coming online this decade will make atmospheric spectroscopy of distant planets more routine, though the discovery that oxygen can form abiotically in ocean sediments has complicated the biosignature search. The next generation of radio telescope arrays will be more sensitive and more comprehensive than anything currently operating. We are at the beginning of an era of revision. What we know now is real. What we think it means is provisional. Holding both truths at once is not weakness. It is the actual practice of science at its best. Carl Sagan wrote in the 1970s that if it is just us in the universe, it seems like an awful waste of space. He was trying to convey a feeling that resists precise measurement, that the scale of the cosmos implies something about its possibilities. That 2 trillion galaxies and 20 trillion candidate worlds and 13.8 billion years of chemical complexity ought to produce something more than one species of primate on one rocky planet, looking up and asking where everyone went. He could not have known that, half a century later, a telescope floating in deep space would provide the most detailed inventory of that space ever assembled. And he could not have known how deeply the images would intensify, rather than resolve, the feeling he was describing. Every image James Webb captures is an archaeological dig through layered time. Every galaxy in the Cosmos Webb mosaic is the past itself, arriving in the form of photons. The scientists studying this data are reading a record unlike anything humans have ever constructed. And what the record shows, over and over, at every depth across every frequency range we know how to search, is a universe that is profoundly, specifically, strangely quiet. The resolution to the Fermi paradox, insofar as one exists in early 2026, is this. The filter exists. It is not a single barrier, but a cascade of attenuating factors, each one reducing the probability of a detectable civilization from the vast population of potentially habitable worlds. The intelligence bottleneck is probably real. The detection window is probably short. The demographic trajectory is probably universal. And the combination of these factors, along with the possibility that we are genuinely early in the universe's civilizational timeline, reduces the expected number of currently detectable civilizations to a number consistent with the observations we have. But this does not resolve whether the filter is behind us or ahead. The data does not definitively answer that. What it does is place us inside a situation with specific characteristics. We are a young civilization, perhaps one of the first. We are in a phase of rapid technological development, the phase that Garrett's model identifies as the most dangerous transition. We are showing the early signs of the demographic patterns that Dugan's model identifies as a universal civilizational trajectory. We have built instruments sensitive enough to begin to hear the universe clearly. We have heard nothing. The resolution lives not in what the universe tells us about other civilizations, but in what it implies about our own choices. If the filter is ahead, and if the mechanisms it operates through are the ones the data suggests, and then the resolution is not astronomical, it is behavioral, it is political, it is the question of whether a civilization can navigate the transition through advanced technology, through artificial intelligence, through demographic collapse, through the political instability of a species that has given itself weapons capable of ending its history without becoming the next null result in someone else's search. The Fermi paradox is not waiting to be answered by a better telescope. The Fermi paradox is already answered, in one direction, by every civilization that made it through. In the other direction, it is answered by every civilization that did not. We are in the process of answering it now. Not with radio telescopes, with the decisions being made in the decades immediately ahead, and Earth has been broadcasting for roughly 100 years. The first radio signals powerful enough to leave the atmosphere date to the early 1920s. Military radar from the mid-20th century, at peak power roughly 10 to the 14th watts in directional bursts, is the loudest thing this planet has ever produced. Those signals expand outward at the speed of light in a sphere that currently encompasses roughly 15,000 stars. A civilization with a Green Bank-class telescope aimed at our star during the right century could detect us. But Earth is already getting quieter. Streaming services instead of broadcast television, digital compression that looks like noise, phased arrays instead of omnidirectional radar. We are moving towards silent. Well, if Garrett's model is correct, and the window between first radio and the civilizational transformation driven by artificial intelligence is roughly 200 years, Earth is approximately 127 years in. The window may be closing from the inside faster than we are opening it outward. If Dugan's model is correct, and the demographic transition limits a civilization's expansive and broadcast phase to 500 to 1,000 years, we are in the first third of that window. The choices made in the next few centuries determine whether the window extends or closes. Two civilizations, both real, both broadcasting, both in their respective windows. The probability of overlap in both time and space, of being within detectable range of each other at the same moment, is the product of two small fractions. The result is very small, The galaxy could contain thousands of civilizations, each burning briefly in their 100 or 1,000-year windows, and they would be as likely to overlap as two fireflies blinking in a forest the size of a continent, each flash lasting a fraction of a second. That possibility does not require the filter to have killed anyone. It requires only that the windows are narrow and the distances are vast, and the galaxy has been producing civilizations at a rate that spreads them across billions of years, rather than concentrating them in the same era. It is the most human of resolutions to the most cosmic of questions. We are not alone. We are just not synchronized. Or we are alone. That possibility has not been eliminated. A sample size of 1, a history of 60 years of searching. It's an observable universe that spans 93 billion light-years. The honest answer to the Fermi paradox in early 2026 is that we do not know. We have better constraints than we did. We have measurements where we had guesses. We have the beginning of a framework where we had only a question. But the question is still open. Every galaxy Webb reveals is a candidate. Every star in every galaxy is a candidate. Every planet is a candidate. And every candidate, until the moment it produces a confirmed signal, is another entry in the column marked silence. FAST is still listening in Gigeot. The Allen telescope array is still scanning. Breakthrough. Listen is processing data 600 times faster than it did 5 years ago. The universe is still expanding, still cooling, still building stars, still producing rocky planets in habitable orbits around stable stars in the middle of stable galaxies, in the middle of a cosmos that has been doing this for most of its existence. And somewhere in one of those 2 trillion galaxies, around one of those hundreds of billions of stars on one of those 40 billion potentially habitable worlds, something might be asking the same question we are asking, or nothing is. And the silence is not waiting to be broken. The question Enrico Fermi asked over lunch in New Mexico in 1950 has not been answered. It has been made more precise, more urgent, more deeply connected to our own trajectory than he could have imagined when he put down his fork and asked where everybody was. The instruments are more powerful than they have ever been. The window, whatever its true length, is still open. Well, we are still here looking. And the universe, for now, is still silent, but not empty. Never empty. 2 trillion galaxies and 20 trillion candidate worlds and 13.8 billion years of complexity accumulating in every direction. All of it watched by exactly one species that built the instruments to look and found enough silence to fill an entire universe, and still cannot decide whether that silence is the sound of being alone or the sound of being early. The answer may arrive in our lifetimes. It may not arrive for 1,000 years. It may be that the answer is already in the data we have gathered, and we are not yet wise enough to read it. What is certain is this: we are the universe that learned to ask the question. We are the matter that organized itself into the shape of curiosity. We are the 4 billion year experiment in chemistry and evolution that produced something capable of looking back at the origin of everything and asking what else is out there. Whether we are alone in that, or simply the first to have built the instruments, is the question that will define the character of the century ahead. The silence is full of it. We begin.